in Europe. I'd like to welcome you all to this afternoon's webinar. This is the second in a series of webinars organized by COGEN Europe under the banner of Power and Heat Boost. Our new series taking an opportunity to investigate and go into further depth on key issues today. A lot obviously is revolved around the European Green Deal. Last month we had our first webinar focusing on the EU's industrial strategy. Today I'm very pleased that we will be talking about smart integration of local energy systems. We have a number of experts from our membership who have very kindly given up some time to participate in this webinar and provide a perspective on sectoral integration, smart sectoral integration of local energy systems. We will have a short overview by Camilla Wachega from Veolia. She's also the chair of our Energy Policy Working Group. And then we will have two success stories. One is the KIEL project, which is integrating flexible power and efficient district heating. From Inyo Jambacher, we have Klaus Parhuber, and then we also have an example from France, the Nice Smart Valley, integrated distributed energy for the Côte d'Azur. And we have two speakers from GRDF, from Gas Réseau Distribution France, Régis Contreau and Philippe Garec. And then after those presentations, we'll have an opportunity for a Q&A. And then my colleague Alexander will give a wrap-up and overview of the issue from a COGEN Europe perspective. Before we start, some housekeeping. So once you've entered the webinar, you're automatically muted. Of course, you can unmute. However, I have a colleague standing by to remute you. The idea is to keep the sound quality as best as possible, so only allowing those who are speaking to speak. So please remain muted unless you're a speaker. You're more than welcome to have your camera on or not. Some of you do, some of you don't. If you're a speaker, you're more than welcome and recommended to stay on camera. Obviously, it's up to you and your bandwidth issue. May you be at home or at the office. Questions will be dealt with in the chat function. So one of my colleagues is standing by and reviewing all the questions that pop up in the chat function. He will collect those and then share them with the different speakers. Just for your information, so you know, this webinar is being recorded. And that is because we actually have a full house today. We're at our maximum capacity. So those who could not attend the webinar or did not have the opportunity to register for the webinar, we will make this webinar available on our website, and that will be promoted following the conclusion of this webinar. And so we can save some time at the end of the meeting for questions. I'll just make a very short announcement that our next webinar, as part of this series of the Power Heat Boost, will take place in June, and it will address the renovation strategy. We don't have a specific date because we're still trying to nail down a number of external speakers as well as someone from the European Commission, from the cabinet, to provide some commentary remarks and reflect on what was said in the webinar, but also react on any comments. Unfortunately, today we weren't able to have someone from the European Commission come and speak. Obviously, it's not very easy. Everyone is quite busy, and there are quite a few competing webinars as well. Hopefully, we'll have someone from the Commission to provide that perspective in our next webinar. Very quickly, so just a little bit about COGEN Europe for those of you who have not run into us yet. We are the cross-sectoral voice of the cogeneration industry in Europe. We work primarily with the EU institutions, so the European Commission, the Parliament, and the member states, and other stakeholder groups in Brussels. Next slide, please. So here is a very quick overview of COGEN Europe and its membership. We're a hybrid organization, European Trade Association. So we have 12 national associations represented across Europe. And then we have over 60 corporate members who represent the entire value chain of the cogeneration sector, starting from the manufacturers, the OEMs, from small, so from kilowatt to megawatt, and their supply chains. And then we also represent the utilities and ESCOs involved in cogeneration. And of course, we also represent a number of the end users using cogeneration. So that's a very quick annotated version of who is COGEN Europe. I'm going to end my intervention now and welcome Camilla to take the floor to talk us through a little bit more about sectoral integration.
Yes. Hi, everyone. Camilla Vacenga. I am chair of the COGEN Europe Energy Policy Working Group. Thank you, Hans, for the introduction. I will just share my screen to make sure that works. Yes. Hope you can see it. Can you see it?
Yes.
Perfect.
You can see it.
Lovely. So I just wanted to introduce shortly our topic and to set the stage for the following presentations that we will have afterwards, with concrete examples of how sector and smart sector integration of local energy systems operate. So very quick reminder, and I think using pictures always help to set the stage and to illustrate the most important transformation that we are facing right now. It's an illustration of the necessary transition of our energy system as a whole. So we've been slowly moving from a centralized one to a decentralized one, with a structure that resembles some nodes of the system around generation sources that are being decentralized further into territory. And now the key challenge that we have is to move towards something much more evolved, which is a distributed energy system. As you can see on the third picture, that it's rather a mesh of various producers and consumers, which means also that consumers are becoming producers, or as they say, prosumers, and where various applications and various solutions are finding their place, including the traditional one, as well as the new solutions that pertain to the realms of what is called end use or flexibility. So the European Commission, as it has been said, is currently working on a strategy to integrate sectors, or to integrate the entire energy system. It is expected to be published by the end of June, by the end of next month. And we have first glimpse into what will go into it. Because the Commission has already published its roadmap and a consultation on this strategy that it's due, and it's due to be closed on the 8th of June. And B, because there's been a leaked version of the strategy that's been circulating last week already, and we could see some points, some elements of the strategy that will probably make definitely to the final document. So the strategy and the whole thinking about how sectors should be integrated is coordinated around 4 principal pillars, and they are energy efficiency first principle, the electrification of demand of the end use, renewables and decarbonized gases that are being more and more integrated, and to be more precise, massively integrated into existing grids and existing systems. And also it should foster links across the energy system, the entire energy system, other sectors, and exploit all synergies that can come across and can be generated if we look at the system as a whole. So smart system integration combines a wide range of energy solutions for an ambitious decarbonization pathway. What is really important is that it has to be achieved at the lowest cost, and also making sure that we have the highest security of supply for all possible consumers, being at individual level or at the level of communities. And this will require, obviously, planning that will be made at the local level, that will optimize investment. It will optimize also all operations and infrastructures to make sure that it's made in a coordinated manner across all energy carriers, sources, and infrastructures. It should also focus on integrated the key sectors, which are the gas, electricity, and heat production and distribution. Our main objective today is to make sure, to show how cogeneration is part of this equation already, and how it can also become the part of the equation in the future. As you can see, cogeneration is already absolutely legitimate solution, given that it transforms 90% of the energy into useful heat and power for all types of consumers. So as a solution, it has its place in the whole thinking and in the whole new energy system, because it enables us, both utility operators, as the company I work for, as well as individual consumer who would use micro CHP, to do more with much less resources. And you can see it perfectly illustrated in the graph, that you can save up to 40% of energy, and primarily of primary energy. You can also cut significantly CO2 emissions and reduce, above all, the energy bills that you might have to pay if you are still reliant on the grid and you cannot produce your electricity and heat on site. So as it's being said, CHP cogeneration today is at the absolute core of the new system that we are aiming at, because it enables us to link both electricity and heat as well as gas markets. It definitely improves the overall system efficiency, making it possible to apply the energy first principle across the entire energy chain. It enables us to minimize waste in all possible forms, being fossil fuels, which obviously will be progressively withdrawn from the new distributed and modern and digitalized system. And it will enable us to integrate such valuable resources as biomethane, hydrogen, and biomass, as well as boosting flexibility by supplying dispatchable power. It will lower the overall energy system costs and bring, above all, value to local level and local communities, new consumers, and potentially create new jobs locally. Yes, so this is just a summary to show you how cogeneration can be part of the new system and why it should find its righteous place in the new context of the new sector strategy. And I will leave the floor to our two presenters to show how practically this can be achieved.
Thank you, Camilla. So now we're going to hear a few interesting stories to illustrate sectoral integration. The first will be the KIEL project. So I have Klaus Parhuber from INEO Jambacher, and he will give the first presentation. I see you there, Klaus.
Thank you very much, Hans. You can see my screen, yeah?
Not yet.
Not yet?
There's always a slight lag.
Now it should work.
Yes. Thank you, Klaus. The floor is yours.
Thank you. Yeah, the KIEL project. KIEL is a city in the north of Germany, and the Stadtwerke KIEL, they were just building a new CHP plant, serving 73,000 customers with heat, and they built a very flexible gas engine power plant consisting of 2 individual units, and they provide power and heat for the city. In addition to that, they have installed a 30 megawatt electrode boiler, the power to heat module, and a large heat storage with 30,000 cubic meters. And by all that, they achieved about 70% CO2 reduction with this new project. This is an animation that was built at the beginning of the project about 5 years ago. You see here the engine hall in the middle, 2 blocks, each 10 units. Every 10 units have a single step-up transformer. Then in the front you see some shop and storage as well as the control room. Then you see 4 chimneys, but actually 5 individual engine chimneys have one envelope, so that the architecture shows just 4 chimneys. Then you see here the electrode boiler behind the pump hall, and in front the big heat storage, which is 60 meters high and contains 30,000 cubic meter of heat. That is about 1,500 megawatt hours of heat storage. This is a picture that was taken end of 2019, right at the time when the plant went into commercial operation. You see here the big heat storage that is just in front of the old coal plant that is here behind it. And on the next here you see them on the left hand side, you see the old coal plant, which was built 50 years ago. It was built really for not flexible operation. Typically such coal power plants have been built for 1 start per year. They shut it down just for some maintenance. The coal plant was also a little bit bigger. It was a little bit more, about 300 megawatt electric output and about 300 megawatt heat output. When running in common heat and power, this plant had, of course, more than 50% total efficiency, but not achieving a fuel utilization and total efficiency of more than 90%, as the new plant is doing. As I said, the new plant is consisting of 20 GEN and 20 gas engines, producing in total 190 megawatt electric output and about 192 megawatt thermal output. On this picture, you see the old coal plant here behind the new engine plant. And really the difference is the flexible operation of the new plants, the gas-fired engine plants, which can start up in 5 minutes and can ramp down to 4 megawatts. Everything between 4 megawatt and 190 megawatt is possible. On the next slide, again, this is a project that is a coal to gas switch, and it is a CHP plant. And in Germany, there are good CHP incentives, and about 5 years ago, the government is providing additional incentives if the customer is switching from a coal to a gas plant. And this makes this project attractive in terms of economics. On the other side, it was a big investment. It was a 290 million euros total investment. It's not only the engine plant. The 290 million has also the pump hall included, the large heat storage, the power to heat module, as I said before, and all the infrastructure around the engine plant. And the customer did go for project finance, and the biggest portion of financing is coming from the European Investment Bank with 105 million euros. And this was possible because this plant is eligible for EIB financing, meeting the EIB lending criteria. Just recently, end of last year, EIB revised their lending criteria and reduced the threshold. Reduced the threshold to 200.
Herr Schmitz, ich bin gerade im Webinar. Könnten wir vielleicht später nochmal?
To 250 grams per kilowatt hour, and the Kiel project achieves 225 grams per kilowatt hour. So making this project also eligible for EIB financing under the new EIB lending criteria. This slide shows you a little bit more about the heating network of Kiel. Here at this point, number one, this is the new CHP plant. There's next to it a heating station. And around the city, there are more heating stations. There's peaking boilers and backup boilers. And there's another CHP plant, which is just a smaller, based on 4 gas turbines, producing about 50 megawatt thermal output. The total heat that is provided per year is about 1 terawatt hour, and the peak load is 500 megawatts. But this is just on very cold days. Yeah, the CHP plant can provide close to 200 megawatt thermal output, 192, and the peak load is then done by the smaller CHP plants as well as by the peaking boilers, which run them just a couple hours per year. And as I said, the off-taker are, the main customers are 73,000 households around in the city. The Kiel project is a highly sectoral integrated project. And on this picture, you see the CHP plant in the center here, running on natural gas that is coming from the local natural gas network. There is also a gas storage nearby. So there's energy storage in terms of gas storage nearby. Then the electricity from the plant is fed into the public network at 110 kV, and there's also supply from the network to the plant, especially to the electrical boiler in times of oversupply of electricity, in times when the renewables are producing a lot of electricity. Then there's the heat storage that is just in between the engine plant and the heat off-taker. And of course, there's a local electricity supply to the consumers, the electric consumers in the city. How does it work? we have decided between two cases, a high wind and a low wind case. At the high wind case, the electricity on the grid is provided mainly by renewables, a lot of wind in north of Germany, and then at this time the engines are not running. Electricity is coming from the grid, and also a heat generation can be done by the power to heat module. If the prices for electricity are really low, and this is attractive to run a power to heat module, this can be turned on, and then they produce green heat out of renewable electricity. And in general, the heat is provided by the heat storage because the engines are not running. And in case of low winds, then the engines are running, electricity and heat is provided by the engine, the heat storage is getting to be filled up. All that is to ensure a stable and reliable heat supply and electricity supply to the customers of the Stadtwerke Kiel. Of course, heat can go up and down. There is a daily load curve on electricity, and there is a difference between winter and summer. But all that demand, heat and electricity, must be guaranteed at any time by the Stadtwerke. And the flexible operation of the plant ensures that this is guaranteed and they can run this plant under the best economical conditions. Flexibility is really key. The flexibility of the plant is shown here again. The green curve shows the electric output of the plant. Here in this case, 20 engines are at full load operating, but then engines can be turned off as needed. Yeah? In this case, it's just an example. Just 10 engines are running, 5 engines are running, or 3, or even just one engine, and the rest is shut down. With one engine running, the plant load is down to 5%, and this engine can even go to part load operation to 50% load. All that with constant electrical and thermal efficiency. So the efficiency of a plant load is not changing. It's always constant at 45% electrical efficiency and 91% of fuel utilization rate, 91% total efficiency. And the engines that are not running, can be brought back online within 5 minutes. This short startup time, short response, fast response, can typically be provided only by plants that are running at spinning reserve. This plant can do it with non-spinning reserve. And this is very important because the plant is operated on the electricity market, and the engines are typically running when the electricity price is good, when the clean spark spread is positive, shown here. If the clean spark spread is negative, engines are not running. Once it turns to positive, engines are started up. And exactly at this time, then the heat storage is very important, because at this time the heat needs to be provided by the heat storage when the engines are not running. And we said before, the heat storage has a capacity of 1,500 megawatt hours. And just to bring this into perspective, what does it mean? If you run the plant at full load, producing 190 megawatt thermal, you need about 8 hours to fill up the heat storage. And in the other way, you can provide heat at full load, full capacity, over about 8 hours out of the heat storage. So the heat storage is a very critical element in the flexible operation of the plant. And this flexibility has been investigated at the beginning, at the project planning by the customer. They did a lot of simulations and modeling. And this chart shows 1 year modeling, and this picture shows 1 day of modeling. It shows that the plant could start up 3 times a day, in the morning, then at noon, and later in the evening. And this was done about 5 years ago. At that time, the break-even to start up the plant was an electricity price of 37 euros per megawatt hour. This is changing from day to day, but at this time, the modeling result was that. And the result was that this plant is designed for flexible operation, and all the engines could see about 800 starts, up to 800 starts per year, with sometimes starting 3 to 4 times a day. Yeah, at the end, we have seen a similar chart before by Camilla. I want to show you this again, what CHP means when you run a gas engine plant. On the left-hand side, you see separate generation of power and heat. And with CHP, you can reduce fuel input by about 33%, saving 33% of CHP, of fuel input, of primary energy input, when running the gas engine plant as a CHP plant. This gas engine plant is producing pretty exact with 2.2 kilowatt hours of gas input, 1 kilowatt hour of heat, and another 1 kilowatt hour of electricity. And very often in Europe, we're using the heat bonus method. This allows us to reduce the specific CO2 emissions from a gas plant from 450 to 225 grams per kilowatt hour. That's how we calculate the CO2 emissions. And with that, we are well below the 250 grams. That is the limit for EIB financing. And as I said before, we achieved 33% primary energy saving, at the same time 33% CO2 savings. That's what I have today. I thank you very much for your attention.
Thank you, Klaus. I suggest we hold off collecting all the different questions until the second presentation. So we now give the floor to GRDF. I'm not sure who is starting, Philippe or?
I will be starting.
Okay, so thank you, Philippe, and the floor is yours.
Thank you, Hans. So hello to you all. Regis and I are very pleased to present you today our Interflex field study on sector coupling with smart appliances. Transition to climate neutrality is deeply changing the world of energy. The challenge we are facing is to solve the world energy continuity dilemma, how to achieve at the same time energy sustainability, energy safety, and energy affordability for all. Successfully, wind and solar electricity are good promises for low cost and abundant renewable energy. The drawbacks are that they are climatic dependent, intermittent sources, and that electricity is the hardest form of energy to store and transport. This is all the more crucial in the prospect of electrifying seasonal demand such as heating. To give you an example, an illustration you can see on the graph here, representing the energy demand in France between summer and winters. The ratio is 1 to 4. One idea to solve this difficulty is through power to gas, a way to take advantage of the existing large gas storage infrastructure. Another one is to use gas grids as a backup at the end user's level through appliances such as mini or micro cogeneration or hybrid pumps. That's what we have tested in Interflex experimentation, which Regis is going to tell you about. Regis?
Thank you, and good afternoon, everyone. So I will be presenting this Interflex project, which is now over because it started in 2017 for 3 years. It's a new European project with a budget of nearly 23 million euros and 20 project partners. And Interflex has been gathering 6 demos, and 3 of them are studying sector coupling. So I've been one of the founder of the French demo, which is called Nice Smart Valley. And Nice Smart Valley is gathering 6 partners to make the locally concrete what we call sector coupling. We can go on through the next slide. Thank you. Okay, so the aim of Nice Smart Valley is to explore flexibilities based on gas appliances at local level. The core of the project was to see how gas appliances, how hybrid appliances and CHPs can support the local network. And in this area, which is in southeastern France, this area is very well known as a bottleneck, as a place where it's very difficult to support grid constraint because of a lack of transmission lines and a lack of power production. So the idea was to use flexibility when there is a constraint on the local grid of the local network to use gas appliances. So first of them was a hybrid heating system. An hybrid heating system is a system where is included a boiler and an electrical heat pump, and it's usually working on regarding efficiencies and outside conditions. Typically, when it's cold, the electrical heat pump is not running at a good efficiency, so the system is naturally switching on the gas boiler. So we've tested 10 of them connected to the power DSO, and we've also tested one hybrid rooftop, which is a larger system, which has been installed on a swimming pool. So the idea is that when there is a constraint, the local network operator send an order to the aggregator, which send an order to the appliance, and if there is not enough power production, the system is switching off from the heat pump to the gas boiler. Same idea for the CHP. A CHP of 70 kilowatts of power output has been installed in Schneider premises, so it's one of their factory. And again, it has been remotely controlled according to the grid needs. So usually the CHP was running at 60% of its power, and then it could be running up and down according to the grid needs. And it has been everything has been developed by the project, so all the energy box and the communication system between the power DSO, the aggregator, and then the appliances. So the first result of this project is that we have been able to validate the qualities of the gas appliances, and especially the CHPs, to offer flexibility to the power system. It can be seen as a bridge, it has already been said, between electrical system and the gas infrastructure at a local level, and even at the global level. We have studied different market values because flexibility can be assessed locally, but it can also be useful globally for ancillary services and what we call the capacity market in France. Technically, the system have answered very smoothly and show very good technical skills compared to the curtailment, which consists in switching off electrical heating, and it's better because of a good reaction time, availability, and the duration of the flexibility. Economically, the value can be assessed from 30 to 90 euros per kilowatt of flexibility per year, and then it will mainly depend on how much electrical renewables will develop on the power infrastructure, For the time being, it's quite hard to imagine a full profitability with this kind of service alone, and it can be only seen as a bonus offer for a CHP. From an environmental point of view, using green gas, because there has been wide certificates of green gas for the gas supply of the CHP, allow to offer a flexibility which is green, storable, and directly encourage the increase of green gas on the gas network and increase of the electrical renewables. And last, socially speaking, the flexibility can be seen as a complementary service to local energy communities that are seeking autonomy and more local energy productions thanks to CHP. So we can imagine a service such as what we call collective self-consumption in France, which consists in gathering consumers around the CHP or local energy production, and then the CHP could also be very flexible regarding the local grid constraint. So we've been quite happy with this project because it has been a proof for us that sector coupling can now be a reality in France. Philippe?
Yes, thank you, Regis. So, as Regis just shown you, Interflex gave us evidences that smart sector coupling at users level is already a technical reality. At GRDF, we strongly believe that coupling of electricity and gas in one energy system at both production and users level is the most sustainable, safe, fast, and cost-effective way to climate neutrality. So, sorry, this is a slide where I try to sum up the interest of coupling. On top, in orange, you have the electric system, with energy production with climatic renewables such as wind or solar, transport and distribution through electric grids with a limited storage capacity, and use with electric heat pump and other uses. On the bottom, you can see in blue-green the gas system with renewable gases produced from organic waste and residues, very much included in local circular economy. So the gas infrastructure with its high capacity transport and distribution capacities and use, which are mostly for heat generation. And in the middle, you have the coupling tools. On the upstream, at the production level, the power to gas and the gas to power, and at the downstream, at the user's level, cogeneration and hybridization of heating equipment. How does it work? To meet the wake trilemma, you must make the most of all resources. One, the cheap renewable and storable gas renewables. Two, optimize the existing infrastructure, especially the electric one, which is very costly. So how to do that? First thing would be to prioritize the direct use of renewable electricity with the limitation, of course, of demand and grid capacity. Two, in case of excess electric renewable capacity, to store the extra capacity thanks to power to gas. And in case renewable electric are not enough to cover the demand, to use the stored renewable gas to meet the extra demand. So then the key to optimize the system will be a smart energy system management will consist in using the best coupling tools according to the instant needs, whether they have to cover needs for heat or not at the same time, whether the electric transport or distribution grid is congested or not. So that's to come to a conclusion. That's why we're convinced that this double coupling is sustainable because it makes the best use of all renewables, whether they are electric or gaseous. It is a safe solution because a dual energy system is by nature more resilient than a single carrier, especially with when considering that decentralized electricity will be produced through cogeneration. Smart coupling secures as well the electric peak management at transport and distribution level, ensuring a higher level of safety and energy safety. It is as well cost effective because it makes the most of existing energy infrastructure by saving the electric peak. The reinforcement can be done at a lesser level and later, highly reducing the overall cost. And even at users level, hybridization can be done by simply adding an H pump on top of an existing boiler. So optimizing the end user's investment. So, and this hybridization will give end user immediate rewards on the bills and extra benefits with every further energy renovation works. Last but not least, it can be done fast. Nothing prevents the installation of mini or micro cogeneration and a hybrid right now. They can be retrofitted in all kinds of existing buildings without the prerequisite of a deep renovation. So our conclusion is that there are truly no regret solutions well adapted for green transition recovery package. Thank you for your attention.
Thank you, Philippe. We do now have time for questions for all sets of the speakers. As I mentioned before, please do use the chat function to place your questions, and the team will extract the questions. I've just sent a text myself on the chat function, so hopefully you'll get a notification and then you can go ahead and ask your questions. As far as I can tell, we don't have any questions on deck yet. If that's not the case, I suggest we give the floor to my colleague Alexandra, who will give some remarks about sectoral integration. Wait a minute, we have one question.
Yeah, and I do have another one as well, Hans.
Thank you, François.
There are some questions popping up now, so thank you very much for populating the chat. But one general question, or maybe two, that came up very quickly were to ask, energy efficiency seems to be an obvious answer when we talk about the energy transition. And every now and then we keep hearing about the importance of energy efficiency. But when we look at the focus, we see that there is a strong focus on demand reduction. I'd like to pick the brains of our speakers today on why energy efficiency is so important when we talk about energy system integration. Maybe giving the floor to GRDF first.
Rajesh, would you like to answer? Oh.
Yes, I can. So the question, François, is why is energy efficiency as important as energy demand decrease? That's it? That's the question?
Yes.
Okay. I would say in my mind, so of course we need to decrease our energy demand because we do know that it will be very difficult to continue to live the way it is, and so we have to decrease an energy consumption. But once it's done, of course and obviously, it's very, very important to use the energy we have the most efficient way it is possible, and even in some case we have to keep in mind that energy efficiency can be achieved in a way which is much more easy than retrofitting. For example, retrofitting multi-family dwellings, a multi-family house is in some cases very expensive and hard to perform. But change a boiler to a more efficient boiler, or to a CHP, or in this example in KIEL, changing a power plant by a CHP is very efficient and not so hard to do. So yes, energy efficiency is very important, I think, and we've got to keep it in mind, because it's not only a matter of decreasing the demand. We have to decrease the way we use the energy, I would say.
Thank you very much, Régis. Klaus from INEO, would you like to add anything to that?
Yeah, maybe one thing, energy efficiency, fuel utilization is something that I think came out of the first energy crisis in 70s, 80s. But I think it is important to don't forget energy efficiency as we transition more and more to renewable energy supply sources, because also in a renewable energy world, energy efficiency is very important. Typically, we have not enough renewable energy available, and this is typically more expensive than the conventional fossil fuels at the moment. So I think in the future it's even more important to consider energy efficiency.
Thank you, Klaus. And that's very important indeed, to make sure we use those valuable resources as fuel of the futures to make more available for other sectors.
I would just would just like to add something, Francois. I think it is very important to have in mind that energy is never free, even if it's renewable. It always has a cost. It has a technical cost. It has a cost regarding resources, raw materials, and so on. So even if our world is going renewable, we still have to use the energy in an efficient manner.
Thank you very much, Régis. A question from the audience here. I mean, in your GRDF, you do have experience in making sectoral integration a reality already today. That will be the case tomorrow as well. Now, you probably face obstacles in the way of developing your project and implementing them. Would you like to let us know also, for the policymakers on the line, what those obstacles are financially, in terms of regulation, and what are the solutions that you see need to be brought forward from your perspective?
That's a very interesting question. So green gases, the thing is, as I mentioned earlier, are kind of included in local economy. They're very much connected to waste management and agricultural residues management, with many positive externalities on, for example, they help agriculture to change their practices to more agroecological practices by developing cover crops, which is good for water quality, which is good for biodiversity. They can produce their own biofertilizers. But all this is not taken into account in the cost of this development of renewable gases. And that give a upfront cost, which is a bit on the higher side. And that's one point. How to take into account the whole benefits that production of biomethane brings to the communities. Another one is that it's difficult to take into account the value of energy that can straight away being stored. And it's hard to compare electricity which is produced and have to be used on the spot, and energy that can be stored for months. And this subtlety in different type of energy is not reflected much in the value at present, because flexibility, as Regis mentioned, is not really a large need now, as electricity is made mostly on dispatchable resources, fossil resources.
Thank you very much. Klaus, would you like to add anything to the barriers you face and would need to be addressed in the future?
Yeah. Well, at the moment, we see a lot of national policies for coal phase out, and ultimately a lot of customers switching to gas, to natural gas. The Kiel project is a good example for it. I think there's still a lot more potential in Europe. Customers are more and more concerned because natural gas is still a fossil fuel and the remaining fossil fuel, and more and more asking questions, what is the long-term future? How can we transition to renewable gases? And I think this is our challenge that is in front of us to ensure to our customers that our solution is also fit for renewable gases. We have, for example, a lot of biogas engines installed, a lot in Germany, a lot in Italy, and around in Europe. But those biogas is very limited at the moment, and it all depends on the availability of biogas, biomethane, and other renewable fuels. So a policy is required to make to ensure that those renewable fuels are available in the future, and customers are investing in sustainable projects. Yeah, they can transfer smoothly from fossil to renewable fuels. I think that is the bigger challenge in the near term.
Thank you very much, Klaus. And there is a question that is very much linking into what you just mentioned about renewable gases. A question from Olivier Guiteny, and I hope I don't mispronounce. What do you think about the role of green gases? Biogas upgrade is mentioned. I assume this could be also covering other types of gases. So what do you think about the role of green gas, grid injection, and their use in integrated distributed energy solutions?
Yeah, good question. One of the use can be seen in the future, as I mentioned, is this green gas, as it's easy to store, can be the green battery for the whole energy system, as you can use it for peak demand, and it's dispatchable energy, which you can use very efficiently with efficient tools like cogeneration and so on. And as Regis mentioned as well, green gas is a very decentralized production. So it gets on very well with energy communities and local energy management.
Thank you very much. Klaus, would you like to add anything, or Regis?
I can add, yeah. As I said before, we have a lot of gas engines running on biogas, converting directly raw biogas to power and heat. But in Germany, we have also customers, they are running their engines on biomethane already today. There is a certain number of biomethane available. I think it's 10 terawatt hours per year. And we have one customer in Hamburg, in the Hamburg area, that's Hanseberg Natur. They run almost all their gas engine CHP plants based on biomethane today already. We are ourselves currently preparing solutions to show our customers what other renewable fuels our engine can run in the future, and that includes hydrogen. that includes mixtures of natural gas and hydrogen and possibly other fuels, yeah, like green methanol, for example. That would be the longer future. But of course, we need to prepare ourselves because we get more and more questions from customers about this type of renewable gases.
Okay, I'm receiving other questions, and there are many more to cover. So I'm afraid I will have to leave the floor to my colleagues to close this webinar and conclude. There is maybe one last question I can put. There is the question of, when we look at the strategy by the European Commission, we see, and when we talk about the integration of energy, especially gases, whether from renewable energy sources, intermittent or not, the big question that comes in mind is, where do we need to use those valuable fuels of the future? Some stakeholders do think that we should use that only in the sectors where there is no alternatives. Others do think that a bigger spectrum of utilization will be important, including buildings, transport, etc. How do you see the reality impacting this question? Maybe Klaus, we start with you.
That's a good question, yeah. First is to make these renewable gases available, and then who are the consumers? And as long as it is a renewable methane, where the physical properties of gas is not changing, it's pretty easy. Everyone can use it as renewable fuels or natural gas because physically it's the same. But once that changes, and this is very much the case when we talk about hydrogen, then it is about producing the hydrogen, transport and distribution of hydrogen, and then convert also the appliances and all the consumer machines to cope with hydrogen instead of natural gas. And this will be a bigger challenge. And for this, I think we need really very sophisticated, detailed implementation plans. Setting a target only is not enough. I think we need really detailed implementation plans for that.
Régis? Or
yeah, I would like regarding that. I would prefer. I think we cannot have a general solution. I'm really not keen to decide something upstream and to say that it should be everywhere the same, because it really depends on the local context. And in some contexts, using biomethane or H2 or hydrogen would be good at a local level. Like use it in houses, use it for mobility, use it for transportation, but and in some other contexts not. So I think we should keep all the options open, and we should have no regret solution, saying that we should keep green gases and some energies on sector where we can use only this energy. It's closing other market and other solution for energy transition. So I would recommend not to do this. I don't know if Philippe, you have something to add to this.
Yeah, I would say that I heard that as well, but I think, as I tried to explain earlier, that to have a wider use of green gases is important for energy safety, so that to have a dual carrier energy system, so that not to depend only on one system. Second point is on affordability. I think, especially for the transition, if we want to go through a higher level of electrification at a say variable cost. We have to find a cheaper solution with what exists already, and this is mostly for heating, at least with a heating system. So the solution is more to have greener gas and electrification than to say it's either one or the other. I think wider is better, and as Regis said, I think for industries we have to go to case-to-case basis and to find out where at some points it can be more interesting to have a specialized use, and where it will be more interesting to have a more widespread and shared utilization.
Thank you, Philippe. Thank you, Regis. Thank you, Klaus. There are other questions I see. I unfortunately, need to pass on the floor to my colleague Alexandra to wrap up and remain within the time frame of this webinar. What we can suggest is that we take those questions and answer those questions in the follow-up of this webinar when we come back to all of you. So that everyone gets an answer to their important questions. Thank you very much to the audience. Thank you very much to the speakers. Alexandra, up to you.
Thank you, Francois. We've heard quite a lot of interesting ideas throughout this session. I will try to wrap up. What we have learned most of all is that cogeneration is a key integration solution for all sectors. So you've seen examples of district heating, you've seen examples of CHP in buildings. We have heard last time about industrial cogeneration, so you can see that CHP helps link electricity, heat, gas systems in the most efficient and most flexible way possible, while addressing a variety of customer needs. So today, cogeneration delivers about 11% of EU's electricity and 16% of its heat, but we know that there's underexploited potential for this solution because by 2030 we have identified that the contribution of CHP can double. And so the additional CHP and upgraded CHP capacities across the various sectors can actually help avoid an additional 315 million tons of CO2. And just to put that in perspective, that's over a third of what will be needed to deliver the additional ambition in terms of CO2 emission reduction. So increasing the CO2 target to between 50 to 55%. So CHP, in addition to the fact that it's an integration solution, it can also deliver high decarbonization benefits. And so looking back to the pillars of the energy system integration strategy, energy efficiency first, electrification of demand, focus on renewable and decarbonized gases while fostering links across the energy system. COGEN Europe has developed a set of recommendations. We are in the process of refining these recommendations and submitting them formally to the European Commission. So this is just a glimpse of our thinking around sectors integration and systems integration. When it comes to energy efficiency first, we definitely welcome the Commission's focus on that. We believe that this will be key for systems integration to be carried out in a cost-effective way. And so we think that energy efficiency should be applied across all energy networks and energy sources, not only to fossil fuels, but also to renewable energy sources. And so CHP should be one of those solutions that is promoted as an efficiency principle. Then moving on to electrification of end use, where we see that the Commission sees there's a potential, especially when it comes to sectors like heating, also road transport. Indeed, that's a trend that is coming. However, we would ask that robust criteria are introduced to promote only renewable and efficient electrification. We know that there are countries with quite carbon-intensive energy mixes with very inefficient power plants that supply that electricity to heat pumps and electric vehicles. This is not what we want to achieve at the end. We don't want to go against our climate objectives with electrification. And so, as we've heard throughout the presentations today, CHP is the perfect partner to electrification because it can produce efficient and flexible electricity when renewable or variable renewable sources are not available. Then when it comes to renewable and decarbonized gases, indeed, we do need a roadmap for the uptake of those energy sources to ensure a higher and faster integration of variable renewables. And we would like to stress that all applications should be developed in this respect. So we should not we should not close the door to heat in buildings utilizing renewable and decarbonized gases, including hydrogen, depending on the local circumstances. And we must ensure that these valuable resources are used in the most efficient way possible, and their CHP is again one of the key solutions. And then overall, we want a more integrated energy system, and so for that we need a long-term strategic planning at the local level, taking into account local circumstances, and integrating infrastructure in an efficient way. Just to give a concrete example, we looking at existing electricity, gas, and heat networks. You should look in a certain district or a certain area to see whether you can integrate waste heat, whether you can modernize the district heating, as we've seen in the KIEL'S project, or whether in that area there is a very well-developed distribution grid network which can be utilized to integrate more renewables and serve the customers with renewable gases. So it's we most of all we need energy integration and energy diversity in order to have a resilient and ultimately carbon neutral energy system. And so when it comes to CHP, we know that it's a key solution, but of course there are barriers to CHP, and so what we'll be working on with our members in response to the Commission's consultation is identifying those barriers and come up with ways of better rewarding the benefits of CHP. Just a few mentioned on this slide. We need fit-for-purpose approaches to allocate energy savings, emissions and fuels to electricity and heat from CHP. We need the better tools to compare CHP with other solutions and identify, again, the benefits. We do need to find ways of incentivizing flexible CHP and maybe promote a higher flexibility of some CHP systems when the applications allow it. And we also need to properly account for the avoided electricity grids costs thanks to CHP, and that will ensure that CHP can play its role as an integration solution. That's all from our side. Back to you, Hans.
Thank you, Alexandra. I'm just going to take this opportunity now to thank all the speakers for their contribution in today's Heat and Power Boost webinar. So specifically, Camilla, our chair of the Energy Policy Working Group, coming from Veolia, as well as Klaus from INEO, Jambacher, and of course Philippe and Regis from GRDF, and also to Alexander for providing some specific insights from COGEN Europe's perspective on the importance of sectoral integration and the potential to contribute further in the future. So we've reached our time, so thank you for everyone's participation. We had a full house, and thank you all for following the housekeeping rules brought out at the beginning, and we look forward to welcoming you again in June's edition of the Power and Heat Boost. We will come out with more information shortly about the exact timing and which speakers will be joining us from COGEN Europe. So thank you again, and I wish you all a pleasant day. Thank you again from COGEN Europe.
Thank you. Bye.
Thank you. Bye.
Bye.
Thank you. Bye.
Bye-bye. Thank you.